Hello, everyone. My name is Bill Curtis. There is a link to my story below. Check it out if you're looking for hope with Parkinson's. The series you are watching is mostly about science. I plan to make several videos that explain how mitochondrial quality control is key to understanding and treating PD. I hope you will get useful information from watching these videos. In Chapter 3, I explain why oxygen is a dual free radical. The implications of this discovery include oxygen not reacting with proteins, lipids, carbohydrates, or nucleic acids. Ground-state diradical oxygen only reacts with other free radicals. Diradical oxygen reacts with iron and hemoglobin, allowing blood to carry oxygen to the tissues because iron is a free radical. Diradical oxygen reacts with copper in complex 4 of the electron transport chain, converting oxygen directly to water. This is due to copper having an unpaired electron. I reviewed free radical chemistry and applied it to the vulnerability of DHA to undergo peroxide chain reactions. Peroxide chain reactions are only possible if oxygen is a dual free radical. I showed the 3 phases of free radical reaction are initiation, propagation, and termination. Finally, I showed antioxidants are simply intermediate products of free radical propagation that happen to be relatively unreactive when they become a free radical by donating an electron to quench a free radical. Also, these antioxidants get recharged with electrons by propagation reactions all the way back to NADPH. If you missed any of this, or if you need to watch it again, you can find the playlist of all the chapters in the comments below. When I left my story at the end of the last chapter, I had pointed out that NADPH is the ultimate provider of electrons to combat free radical propagation. Just as the unique properties of oxygen, which are only understood if one sees oxygen is a dual free radical. One can only understand the role of NADH and NADPH if you understand why they have different redox potentials. So, I am going to take you on a brief tour of history and tell you about the person who discovered NADH and NADPH had different redox potentials. That is none other than the late Richard Veech. Here is a recording I made of him explaining how he discovered that NADH and NADPH have such different redox potentials.
So I went to the lab. I got there from the airport about 8:30, and walked into Krebs's office, and he assigned me the task of doing the NADP-NADPH ratio because he'd just done the NAD-NADH ratio in the mitochondria. And at that Weber conference in Indianapolis, George Cahill asked him what the NADP-NADPH ratio was. So Krebs assigned that topic to me. First year, he'd talked to me. It was very nice, but we never talked about the work. It was only when I brought him the answer, and he didn't think the answer was right. And so then he, again, didn't talk to me about it. And then after he thought about it for 2 weeks, then we started writing the paper. And that was the longest paper he ever wrote. It took us about 2 or 3 months to write that paper. Well, Pat Lund was the one that trained me and told me how to do, and taught me how to do enzymatic analysis and whatnot. When I finally got the answer of what the NADP-NADPH ratio was, I couldn't get the glutamate dehydrogenase reaction has unequal terms, and it has alpha ketoglutarate ammonia divided by glutamate. So since you're doing them in micromoles per gram or millimolar, it gives you an error in that unequal constant of 10 to the 3, and I was getting off in the calculation by 10 to the 3 because that reaction has an unequal number of metabolites, and Pat's the one that pointed that out. Now once it pointed that out, then it all fell into place. So one day I said, well, Pat's better than these professors. Why don't you give her a degree? And he said, all right.
Why can't one measure total NADP?
NADP is in the cytoplasm and in the mitochondria and also bound. It's a total measurement of something that has no thermodynamic meaning. You want the NADP in the compartment of interest, whatever you're interested in, the cytoplasm or mitochondria. If you measure the total NADP, it doesn't tell you anything because it's made up of at least 3 different components. cytosolic, mitochondrial, bound. So it's just a composite number that has no meaning. If you measure the NAD and NADH ratio in whole liver, it's about 5. But the cytoplasm is about 500 to 1,000, in fact, and the mitochondria is about 5. So it has no real meaning, and it doesn't change between fed and starved.
Richard Veech measured the ratio of NADP to NADPH. If you look at the ratio of NAD plus to NADH, it was 1164. The ratio of NADP plus to NADPH was 0.014. These two ratios vary by 8.3 times 10 to the fourth. That is about 5 orders of magnitude difference. This difference was unbelievable to Hans Krebs. What do you think Krebs was thinking for 2 weeks that turned the lights on in his head and led to this fury of 2 or 3 months of writing? One thing that Krebs knew like few others was all of the reactions of NAD plus and NADPH. I am going to speculate that Krebs figured out that there were 2 sets of reactions that were determined by 2 sets of enzymes. One set of enzymes recognized the phosphate group on NADP. One set of enzymes recognized the lack of phosphate group on NAD. Let's take a look at the difference between respiration and the Calvin cycle. The Calvin cycle is where plants take 24 electrons harvested from the sun by NADPH and add these electrons to CO2 to make glucose. In respiration, which consists of glycolysis and oxidative phosphorylation, 20 out of the 24 electrons from glucose are accepted by NAD+. Why is NAD+ used to pick up electrons in respiration? Why is NADPH used to drop off electrons in the Calvin cycle? The 2 sets of enzymes have a very grand orchestration not too different from an airport. The lack of a phosphate is used by one set of enzymes to send the NAD+ to the arrival lane empty, while the presence of a phosphate used by the second set of enzymes sends the NADPH to the departure lane full of electrons. Enzymes direct NADPH to the Calvin cycle where the electrons are dropped off to make glucose out of CO2 plus 24 electrons, all from NADPH. NAD+ arrives empty to pick up 4 electrons from glycolysis. Inside the mitochondria, the ratio was only slightly favorable for NAD+ to pick up electrons from pyruvate and also from the Krebs cycle. Recall this was 7.7 to 1 and had recently been determined by Krebs. Could this be because the ratio of NAD+ to NADH could not be too favorably empty, or NADH could not drop these electrons off in the electron transport chain? In order for NAD+ to pick up electrons from glucose in respiration and for NADPH to drop off electrons in the Calvin cycle, they must have different redox potentials. What can we explain by knowing these ratios are so extremely opposite? Photosynthesis, respiration, the neurotransmitters in our brain, plants making food from CO2, water, and ammonia, people storing food as fat, and protection from free radicals all depend on oxygen being a dual free radical and NAD having a different redox potential from NADP. Now you know. I am going to quit now and talk next time about how superoxide is made and how it is broken down.